I want to welcome everyone to the next session, the NHERI Site Introduction Panel session. We will get started in just a moment.
Good morning, everyone. Robin, can you hear me? Awesome. Hi, Lori. It's nice to see everyone. So next up, you all talked about learning more about, as part of your goals, learning more about NHERI and all the sites and what they have to offer. So we actually have representatives from all of our sites, including our social science site Converge, with us today. I'm going to introduce what we call the NHERI wheel, and it's all of the sites that are there. First of all, let me introduce myself again. So just real quickly, my name is Karina Vielma, and I am an assistant professor of engineering education at UTSA. And so I work with very interdisciplinary engineering across the college as well as education. And my research focuses on access and equity in engineering education. So being able to promote more inclusivity and access for women, underrepresented minorities into engineering fields. So I'm very happy to be here with you. I've been working with NHERI for the past 5 years as a postdoc before I became an assistant professor. And this is an amazing network to be a part of. And like Joanne said, now you all as Summer Institute participants will now be, at the end of these 2 days, you'll be alumni and will be incorporated into this network. Robin is also going to help to lead some of she's our education specialist, and so she'll help to also introduce the sites. And so so as we've talked about, NHERI is a distributed national facility, and these sites are all across the United States in different areas, different universities, focusing on different hazards, very interdisciplinary as well. But we want to show you, and if you can go to the next slide, Robin. These are all of the sites, and as well as the NSF award. So each site has their own NSF award with their own components, intellectual merit and broader impacts for each of the sites. And so you can see that we have the Sim Center, which is located at UC Berkeley, and they focus on computational simulation. So I'm starting at the top of the wheel here, and then going around. UT Austin has 2 sites. One of them is Design Safe, which is the cyber infrastructure, and they have they're the ones that keep all of the data housed in these beautiful mainframes. If you ever get a chance to go visit the Texas Advanced Computing Center, which is home to Design Safe, they will take you on a tour and show you all of these mainframes and this cooling system that they have to keep it cool, because as you know, Texas gets hot and these big machines create a lot of heat. Lehigh has the large-scale multi-directional hybrid simulation testing site, and they also work with very cross-disciplinary, interdisciplinary with other sites. University of Florida has the wind experimental facility with wind simulation, and Florida International University also has the Wall of Wind, which is an international hurricane research center. Our REU students have gone to also visit FIU and present there for the very first summer that we had REU students. UC San Diego has the large high performance outdoor shake table, and they also have their REU students, they build, sometimes they'll help build or put in all the accelerometers, all the instrumentation into these buildings. And students really enjoy being out there with their hard hats and getting to work at the facility. UC Davis has a geotechnical centrifuge, and UT Austin. So this is the second site. They have mobile shakers that travel out to wherever you need the shaking to happen, whether it's on a bridge or in a certain area of the a certain region. And they've brought out their shakers as well to the Summer Institute when pre-COVID to show us a demonstration. So we got to feel the shaking underneath our feet. Oregon State University OSU has the wave basin and flume, and we also have had our RE students go out there and visit and see some simulations of how those waves happen. It's incredible. And the University of Washington has the rapid facility with post reconnaissance. They have a lot of cool toys that if you're ever able to get into one of the workshops, they'll show you how to use them. And in fact, they will send them out, ship them to you if you're doing post-event research. And we also have the University of Colorado Boulder with Converge. This is our social science component. And when we talk about engineering research, all of these affect human lives in some way. And so it is so critical to have that component as part of your research. So when you think about your own proposals, think about how you might want to incorporate the social science component into your proposals. It makes them a lot more engaging and a lot more competitive as well. And lastly, I can't see the last one, but is that the Network Coordination Office? That's us. So the Network Coordination Office is housed in Purdue University, and that includes the education and community outreach component, which is housed here at UTSA, as well as other components of leadership that help to bring the entire community together. And we talk, have meetings, all the PIs have meetings across the network and talk to each other. So this is a great network to be a part of. Welcome to it. And we hope that you will learn more about how to use the facilities so that you can incorporate them into your own research in the near future.
The NHERI Wall of Wind at Florida International University is an NSF-funded facility that enables researchers to better understand wind effects on civil infrastructure systems in order to prevent wind hazards from becoming community disasters. The NHERI WOW experimental facility is powered by a combined 12-fan system capable of repeatable testing in up to 157 mile-per-hour wind speeds. One advantage of the facility is the multi-scale and high Reynolds number simulation using 12 fans and a water spray system, which demonstrates the effects of wind and wind-driven rain. The 16,000 square foot fenced-off secure area enables researchers to plan and perform destructive tests for up to Category 5 hurricane wind speeds. Using a wide range of equipment, instrumentation, and experimental simulation protocols, the distinguished group of faculty, staff, and the well-trained team of technical and operations personnel are ready to support your world-class research. The Wall of Wind offers the following testing: high-speed holistic testing with simulated wind speeds, including Category 5 hurricane, destructive tests to study failure modes, wind-driven rain simulation to study water intrusion, full and large-scale aerodynamic aeroelastic testing and atmospheric boundary layer flows, extreme environment testing to develop innovative mitigation devices, and conventional boundary layer wind tunnel testing. If you are interested in learning more about the resources at the NHERI FIU Wall of Wind Experimental Facility and how they can support your research, contact Arindam Chowdhury. The Hinsdale Wave Research Laboratory was established at Oregon State University in 1972 with the construction of the Large Wave Flume. The lab is the largest nearshore experimental facility in the United States. Researchers from around the world use the facility to examine the effects of wave, wind, and coastal hazards on a variety of structures and coastal areas. The purpose of the research conducted at Hinsdale is to improve the resilience and sustainability of coastal areas, as well as develop innovative solutions to the design of coastal infrastructure. The Large Wave Flume and Directional Wave Basin allow for researchers to explore coastal and nearshore processes, such as nearshore hydrodynamics, tsunami research, coastal structures, sediment suspension and transportation, environmental fluid mechanics, and floating structures. The lab also hosts collaborative projects. One such project, pictured here, is the Wave, Surge, and Tsunami Overland Hazard Loading and Structural Response for Developed Shorelines by Kennedy, Gainham, Barbosa, and Cox. This project created new tools to predict structural damage from inundation events along developed shorelines using computer-based predictive methods. Hinsdale also hosted the NSF Career Award research from Andrew Myers, which focused on advancing multi-hazard assessment and risk-based design to promote offshore wind energy technology. If you are interested in learning more about the resources at the Wave Research Lab at OSU, contact Hinsdale at oregonstate.edu.
The Design Safe Cyber Infrastructure is part of the NSF-funded Natural Hazard Engineering Research Infrastructure. It provides a web-based platform to enable transformative research that protects human life and reduces damage during natural hazard events, such as earthquakes, windstorms, and floods. As these events become more common and more destructive, Design Safe aims to amplify and link the capabilities of natural hazard researchers in the U.S. and abroad. The Design Safe Data Depot provides private and public disk space to support research collaboration and data publishing through a web interface. The Design Safe Reconnaissance Portal uses a map interface to provide easy access to data collected to investigate the effects of natural hazards. And the Design Safe Workspace provides cloud-based tools for simulation, data analytics, and visualization, as well as access to high-performance computing. There are many examples of how design-safe data and tools are being used to enhance our understanding of the effects of natural hazards on the built environment. Detailed data and images of damaged buildings have been collected by many groups of researchers after events such as Hurricanes Harvey and Michael. These data have been published on Design Safe and are being used by the broader engineering community to better understand hurricane impact and to use artificial intelligence to better predict potential hurricane damage. To better understand the impact of a magnitude 9 earthquake on the city of Seattle, researchers at the University of Washington and the U.S. Geological Survey used design-safe computing resources to perform regional ground-shaking simulations. These simulations incorporate the unique deep sediment structure in Seattle, which affects the characteristics of shaking and can be particularly damaging to tall buildings. The results from these simulations are available via Design Safe and are being used in the design of high-rise buildings in the region. These are just a few examples of how the capabilities of Design Safe are enhancing natural hazards research and becoming an integral part of research discovery. Learn more or join our community at designsafe-ci.org.
Much of the world's population lives in regions susceptible to earthquakes, hurricanes, or other natural hazards where the risks are compounded by aging buildings and civil infrastructure that often are not designed to resist the hazards. While experiments and field observations are used to understand the impact on communities, computational simulations are an essential component of the science and engineering needed to evaluate and mitigate the potential devastating effects of natural hazards. To advance these capabilities, the NSF-funded Computational Modeling and Simulation Center, or SIM Center, serves the natural hazards community as an essential and central resource that provides next-generation computational modeling and simulation software tools, user support, and educational materials. The SIM Center's goal is to advance the nation's capability to simulate the impact of natural hazards on structures, lifelines, and communities. Headquartered at UC Berkeley, the SIM Center relies on a diverse team located throughout the country with expertise in structural and geotechnical engineering, computational fluid dynamics for wind and water, earthquake and wind engineering, performance-based engineering, social science, state-of-the-art computer science, and software development. The SIM Center addresses these diverse hazards and disciplines by producing flexible and reconfigurable software applications that researchers and practitioners can use to better understand the effects of natural hazards on the built environment. These applications enable the SIM Center to achieve these goals. 1. Provide tools to interface with outputs from the hazards science community. 2. Advance local-scale computational modeling of buildings and infrastructure subjected to natural hazards. 3. Facilitate regional-scale risk simulation with multi-fidelity, high-resolution models and data. 4. Develop tools for integration with social science and urban planning models. And 5. Engage and educate the natural hazards engineering community to advance simulation methodologies and their use. Emerging researchers are trained through workshops, webinars, and programming boot camps. The state-of-the-art in computational simulation is published in a recent report which includes how tools developed by the SIM Center incorporate advanced simulation methods, uncertainty quantification, cutting-edge artificial intelligence techniques, and high-performance computing. The report outlines how the research community can leverage these tools to advance research in various areas of natural hazards engineering. Through its emphasis on multi-hazard and multidisciplinary approaches, the SIM Center benefits the broad natural hazards engineering community. We foresee that policymakers worldwide will be able to rely on researchers' integrated simulations to make vital decisions to mitigate the social and physical damage from natural disasters, thus creating more resilient communities. For more information, visit the SIM Center website and join our community.
The Center for Geotechnical Modeling is located at UC Davis. The center is operated and managed under the direction of Dan Wilson and Ross Boulanger. The research performed at the center is to advance the ability to predict and improve the performance of soil and soil structure systems affected by earthquake, wave, and storm surge loading. This is done by scaling the stress in a model specimen using the radial G-field produced by a centrifuge. The main equipment at the facility consists of a 9-meter centrifuge shown in the lower left, which has the largest shake table in the world, and a 1-meter centrifuge shown in the lower right, which can be used for pilot studies. Both centrifuges are supported by a large and diverse set of equipment that can be used to build models. The facility is spread across 3 separate buildings, moving from left to right. The prep for the 9 and 1-meter centrifuge is done here, as well as housing of the 1-meter centrifuge. Located in the middle building is electronics and sensor calibration, and then finally over here on the right is a 9-meter centrifuge, which is located beneath the ground. For those of you who have not seen how a centrifuge operates, here is a sketch of the 9-meter centrifuge. The centrifuge rotates around this spindle, which is shown here in the center. As you rotate faster and faster, the bucket starts to tilt up, and when you get to 75 Gs, the bucket is near vertical. The G-field produces a normal stress on your model, and an actuator located down here at the base can simulate shaking of the model and any structures that you may have on top of the model. Here's an example of a recent project that used the 9-meter centrifuge. In this experiment, the system-level performance of building foundations founded on MICP improved zones overlying liquefiable sand deposits was investigated. This experiment was designed to understand the effect MICP had on reducing total and differential settlement. The study did show that MICP had an effect at reducing settlements and damage to buildings. Thank you for your attention. For any additional information about the center, please visit our website, which is shown here below.
Hello, everyone. I am Joel Conte, the PI of the NHERI at UC San Diego Experimental Facility, which consists of a large high-performance outdoor shake table, which was commissioned in 2004. For 15 years, we have used it as a 1 degree of freedom shake table. The table is now under upgrade for 6 degree of freedom capability. It will reopen in October 2021. And with the upgraded shake table, we'll be able to investigate in full 3D and at large or full scale the combined effect of realistic near-field translation and rotational ground motions applied as dynamic excitation to structural, geotechnical, or soil foundation structural systems, including the effect of soil structure interaction, nonlinear soil and structural behavior, and soil liquefaction. You see here some large-scale and full-scale specimens that were tested in the last 15 years. Many building specimens out of reinforced concrete, pre-stressed concrete, timber, metal. You can see utilities. We can also use the shake table in combination with large soil boxes to test geostructures, such as retaining walls here and here. And finally, here we have the NHERI at UC San Diego team, consisting of a number of faculty members with expertise in various aspects of earthquake engineering, with 20 years experience in running this facility. We also have very talented research and development engineers and technicians ready to help you plan, design, and conduct your future experiments. We can be contacted at this general email here, and more information can be obtained on our website at the Design Safe. Thank you very much for your attention.
Hi, my name is Lori Peak, and I am the principal investigator for the National Science Foundation supported Converge facility, which is headquartered at the Natural Hazard Center at the University of Colorado Boulder. Converge was established in 2018 as the first social science-led component of the Natural Hazards Engineering Research Infrastructure, or NHERI. Our team consists of full-time researchers and graduate and undergraduate students here at the university, as well as a global network of partners from across many disciplines. Converge brings together networks of researchers from geotechnical engineering, the social sciences, structural engineering, nearshore systems, operations and systems engineering, sustainable materials management, and interdisciplinary science and engineering. We support and advance research that is conceptually integrative in an effort to democratize educational opportunities and the research process through a 5-step convergence framework. First, we identify researchers through connecting and collaborating with the 7 NSF-funded extreme events research and reconnaissance networks. Second, we are working to accelerate the education of a diverse next generation of hazards and disaster researchers. To that end, the Converge team has developed a series of training modules that cover a wide range of topics, including, for example, social vulnerability in disasters, disaster mental health, cultural competence, and emotionally challenging research. Third, Converge is dedicated to developing a research agenda for promoting problem-focused and solutions-oriented convergence research in the hazards and disaster field. Fourth, Converge works to connect and coordinate functionally and demographically diverse research teams. Converge has established the first leadership core for extreme events, reconnaissance, and research that brings together the leaders of the NSF Extreme Events Research Networks and the NHERI facilities that support reconnaissance efforts. Finally, Converge supports and funds convergence-oriented data collection, data sharing, and solutions implementation. We have funded researchers to study the impacts of the COVID-19 pandemic, the recent California wildfires, hurricanes, and other extreme events. These 5 key activities and the many other efforts of the Converge facility are designed to ready researchers to both assess and address the many pressing social, economic, environmental, and technical challenges that lead to disaster losses. For more information about Converge programs, activities, and publications, please visit converge.colorado.edu. Thank you.
The University of Florida proudly hosts a shared-use NHERI experimental facility that enables transformative wind hazard research. Our globally unique boundary layer wind tunnel is located within the 20,000 square foot Powell Family Structures and Materials Laboratory. The UF NHERI PIs and staff help guide researchers through the process of vetting project ideas, writing proposals, conducting experiments, and identifying outreach opportunities. The wind tunnel simulates atmospheric flow conditions at a reduced geometric scale. We have developed several features that dramatically increase experimental throughput. The terraformer is a unique system that controls the height and aspect ratio of more than 1,100 individual roughness elements, providing unprecedented granularity in the control and tuning of approach flow. In less than 90 seconds, the roughness configuration can be changed to alter the boundary layer profile and geometric scale. A suite of instrumentation is available to monitor flow velocity and test subject pressure, base reactions, and motions. Turbulent flow is measured using Cobra probes mounted on a 3 degree of freedom instrumentation gantry that can traverse nearly the entire length, width, and height of the wind tunnel. The gantry is also fitted with a stereoscopic particle image velocimetry system, or PIV. Its energy laser illuminates particles that are dispersed into the flow, while 2 high-speed cameras capture the particle motion to produce 3-dimensional, time-resolved flow field measurements. The simulation of non-neutral and non-stationary flow is achieved by our flow field modulator, or FFM. The FFM slides into the wind tunnel on a track system upwind of the terraformer. This array of over 300 individually controlled fans can produce non-monotonic flow profiles and impart transient gusts characteristic of field-measured extreme wind events, enabling new investigations in wind structure interaction not possible in a traditional boundary layer wind tunnel. Please contact us to initiate your wind hazard research. We're looking forward to hosting your NSF projects in our NHERI experimental facility.
The NHERI at UTexas Large Mobile Shaker Facility is located at the University of Texas at Austin. We are home to 5 large mobile shakers and associated instrumentation, including data acquisition systems, geophones, 3-component broadband seismometers, a fiber optic distributed acoustic sensing interrogator, 3-component nodal seismic stations, and cone penetration testing equipment. While our equipment is stored in Austin, Texas, our mobile shakers can be taken anywhere in the world to conduct in situ dynamic testing of civil infrastructure and natural geologic systems. These in situ testing capabilities are essential for evaluating existing infrastructure in actual field conditions that are difficult or impossible to replicate in a laboratory. The NHERI at UTexas science plan revolves around 3 main research thrusts. First, non-invasive subsurface imaging from 1D to 3D. Second, in situ liquefaction and nonlinear testing of soils. And third, soil structure foundation interaction and structural health monitoring studies. Some example projects include in situ nonlinear testing of bioremediated soils engineered to reduce liquefaction potential. Here, the T-Rex and Rattler large shakers were paired together to induce higher levels of shear strain deeper in the soil at a site near Portland, Oregon. Here, the triaxial T-Rex shaker was used to non-destructively test a bridge in New Jersey to characterize soil foundation structure interaction under large amplitude shaking. In another project, the shaker from our smallest truck was removed and mounted on a scale building model to simulate dynamic loading on a structure atop a newly developed seismic isolator. For more details on our equipment and videos from past workshops, please visit our website at utexas.designsafe-ci.org.
The University of Washington in Seattle hosts the NHERI Rapid Natural Hazard Reconnaissance Facility. The mission of the facility is to provide investigators with the equipment, software, and the support services needed to collect, process, and analyze perishable data from natural hazard events. The facility emphasizes three-dimensional, image-based, advanced survey data to serve a range of disciplines. Some of our most requested equipment includes tripod-mounted terrestrial LiDAR systems capable of scanning ranges up to 2.4 kilometers for landscape scale mapping, as well as smaller and extremely portable systems with a 130-meter range. The unmanned aerial Phoenix Mini Ranger LiDAR system, customized to meet the needs of the rapid and natural hazard reconnaissance community. 2 Street View camera systems with car and backpack mounts for post-disaster image capture. And a 2-meter-long autonomous survey boat for collecting bathymetric data. In addition to instrumentation, RAPID also provides reconnaissance advisory services and basic logistics support for field investigations. We respond globally to disasters and to field data gathering projects across the world, so we can help you get your equipment where it needs to go. You can find more information about the equipment portfolio, software, and services on our website at rapid.designsafe-ci.org. We are committed to reconnaissance-based science, shared resources, open data, interdisciplinary research, community engagement, and innovation to reduce the adverse impacts of natural hazards. Please don't hesitate to contact us if you have any questions about the facility or about what we can do to help your NSF project.
All right, thanks so much for watching each of those videos. We'll hope you'll consider what sites you will use when you're talking about the science plan and as you're doing your proposals moving forward. I want to quickly introduce the different individuals we have here representing each of the sites, and then in the time remaining, we're going to give you the opportunity to speak with them and ask them questions. So let me go ahead and introduce these individuals. Let me put this in presentation mode. From Florida International University, we have Dr. Arindam Chaudhry and Dr. Stephen Diaz. From Lehigh University, we have Dr. Jim Rickles and Dr. Liang Cao. From the OH Hinsdale Wave Research Laboratory, we have Dr. Pedro Lamonaco and Dr. Lindsay Carroll. From SENS Center, we have Dr. Frank McKenna and also Dr. Laura Lowe's. From the Center for Geotechnical Modeling, we have the University of California, from the University of California, Davis, we have Dr. Ross Bolanger. From the University of California, San Diego, we have Dr. Gilberto Mosqueda, Dr. Quresh Latsvitsa. From Converge, the University of Colorado Boulder, we have Dr. Lori Peak. From the Powell Laboratory at the University of Florida, we have Dr. Kurt Gurley and Dr. Jennifer Bridge. And from the Large Scale Mobile Shakers at the University of Texas at Austin, we have Dr. Tricia Clayton. From the University of Texas Austin Design Safe Cyber Infrastructure, we have Dr. Tim Cockrell. And from the Rapid Response Research Facility at the University of Washington, we have Dr. Joseph Wortman. So in the next about 15 to 20 minutes, we're going to take questions not only from our in-person attendees, and Karina will take those questions in the room, but also from our virtual attendees. If you will type those in the chat, I will also field those. I'm going to go ahead and turn it over to Karina right now, who's going to field questions from in-person. Again, if you have questions, you can also type those in the chat and I will share those as well.
Robin, can you hear me? Okay, great. Yes. Okay, for Sim Center. So for Sim Center, the question is, they've seen a lot of publications with earthquake research, and our Summer Institute participants wants to know if you are expanding to other hazards like hurricanes and coastal hazards, any other natural hazards.
So this is Laura Lowe's. I'm representing the Sim Center this morning. Frank was not available to participate. Yes, absolutely. The Sim Center has a number of tools that are appropriate for the wind research community. Right off the bat, there's the WeUQ application that allows you to do introduce uncertainty into simulation of wind action on structures. There's HydroUQ that does the same thing. And then we've developed a couple of regional testbed projects that are embedded in the R2D application as well. And those testbeds are for Lake Champlain, the New Jersey coast. So those are all hurricane events. And there's a significant amount of work that's being done on the tsunami side as well. So absolutely goes beyond earthquake. I would encourage you to take a look at the website and kind of go through some of the different applications. There's a lot more information there. Thanks, Tim.
Thanks, Laura. Yes, we have another question for the rapid facility. So for rapid facility, can the scanning equipment go below ground and not just above ground? Do you have scanners with those capabilities?
Our laser scanner portfolio is largely terrestrial. So they're tripod mounted laser scanners. We do have subsurface ground investigation equipment. Specifically, we have a MASW system, and as well as seismometers that can be used to understand soil profiles and the makeup of the geotechnical condition around sites, and we can absolutely talk to you about how those might be used for what your interests are. The scanners don't have to be connected to GPS, so using them in tunnel situations is fine, but they're not meant to be, they're not ground penetrating. Oh, Katerina, I think you're muted.
I'm asking our participants to come up. I think it's a lot better. I hope that's okay.
Yeah.
Hello, thank you. So it's actually related to the previous question. So I'm wondering if, the LiDAR system can be connected to a drone, or it should be always, like on a tripod.
Yeah, thanks for the interest. And so we have one of our kind of key pieces of equipment, I would say most used pieces of equipment, is actually a Phoenix Mini Ranger system, which is a drone mounted LiDAR system that is specially put together actually it's a mobile LiDAR unit that is mounted to a drone. And we do a lot of work with that. It's a highly requested piece of equipment. And we'd be happy to share example data sets and talk to you about the capabilities, accuracy, resolution, flight times, and things like that. That is the one piece of, or one of two pieces of equipment that requires a rapid staff member to operate. So it is a little bit costlier sometimes to use the system, but still we see projects, in the, still we see reasonably costed projects get out and use the Mini Ranger system without a problem. But it does require a staff to, it's a really complicated system, so it does require staff. Maybe I'll just correct too, so people can know who to contact and stuff. So Joe Wortman is the director of the facility. I'm Jeff Berman. I'm the operations director of the facility. And many of you may or may not know me.
Thank you, Jeff. We have another question. Yes. They can hear you.
I'm sorry. Hi, Jeff. This question is for you again, too. So I have a question about the existing data that exists from different rapid reconnaissance missions. I found it. I've noticed it's several terabytes in size. Do you have any suggestions for how to, for each site? How do you, what suggestions would you make for somebody who is interested in just downloading that data and making georeferenced maps of what's been collected so that we can get a look at how these things can be processed?
Yeah, that's a great question, and one of our kind of big emphasis areas for the kind of next 4 years of operations here is to kind of help with the reuse of the data that's been collected in reconnaissance and is stored on DesignSafe. So we're working with DesignSafe right now. They've just launched HazMapper 2.0, which is I think a really great way to map and kind of look at the data sets that are public on DesignSafe and in a georeferenced format. So that's maybe a good starting point. We know there is tons of data that is collected by the Rapid and put up, and that's Street View data and all this other stuff. And so we're also working with DesignSafe, and you should see it launched fairly soon, that there will be a Street View. You'll be able to launch Street View from HazMapper. And so you'll be able to view all those Street View collected data sets. And there's many of those, notably from just about every hurricane. And so those will be, I think, a lot easier to view. And then the download process, it is a lot of data, and there's just not a great way to grab terabytes of data from really any resource online, right? So I think working with DesignSafe, if you are going to be a heavy user, they can give you, you can work with DesignSafe on DesignSafe Slack, and they can give you, assistance with Globus download of these big data sets. And that's what we use to actually push our big data sets up to DesignSafe. So I would encourage you to reach out. They're very, helpful in developing kind of customized solutions, especially for researchers that sounds like you who want to do these kind of large scale analyses and do need to download these really big data sets. So certainly challenges, but I think we're all here to help you overcome them. And just, I would say, reach out and we'll come up with some solutions.
Thank you, Jeff. We have another question. Go ahead. Let's see.
It's for Jeff and a person concerned at the UCSD facility. So there are a number of equipments listed. Some are very commonly used equipment. Are there any wait times for using it? What are the common wait times for different equipments?
For the Rapid or for UCSD?
For the Rapid, and yeah.
No, so we typically are able to, I'll phrase it this way. We have not had to turn down a single request in our operations for any requests for equipment. We may have to kind of reschedule things a little bit. Sometimes we do things like in-field handoffs between teams, or sometimes we need creative solutions, but we've been able to accommodate every request.
And at the UCSD facility, I believe large scale experiments are done on the shake table. So how much I'm sure there must be a lot of experiments being done. So if I want to schedule an experiment, how much time it takes to have that thing in process?
So I could take that. I know we have Dali Vandenaida and also Karush from UCSD, so you could feel free to add on. But experiments, as you noted, are very large scale, and they could take, well, overall years to complete the test, starting from proposal preparation. And so usually early on in the proposal process, you talk with the site and get and talk about the scope of the project, and to make sure you're within the capabilities of the table. And once you receive the award, you can start looking into reserving the spot, because they're usually about, maybe you could have a year or longer queue in the process.
Okay. All right, that's the questions I had. Thank you.
Thank you, Jeff and Gilberto. Are there other questions from the room? One more question? Yes, if you don't mind coming up. Robin, do you have any questions as well outside? I mean, in virtual,
There
online?
have been no virtual questions up to this point. Feel free to put them in your chat if you have a question.
Okay.
Yeah, so I wondered, if you could, if you have any, servo controlled, hydraulic actuators that can be used for hybrid simulation in combination with the shake table testing, facility, if you could, combine, some outside, hydraulic actuators with the shake table to test, like an abutment or something.
So yes, we do have, we do have the hybrid testing capabilities within the shake table. I should note that we're currently undergoing an upgrade to 6 degrees of freedom, as you're probably all aware. And in the previous configuration, we did have one actuator available. But as we go through part of the upgrade, we have the availability to use actuators from our other existing labs on campus. So we do have that capability to be able to combine the shake table control system with external actuators. And we have a combined control system connected to the ScramNet for that.
Oh, okay, so those actuators can be, like put on a setup, like next to the shake table, right?
Yes, and driven synchronously.
Great, thank you.
Yeah, sorry, let me add something. At Lehigh University, we have a shake table as well that we've added here. It's under construction. And we can do hybrid simulation. In fact, we'll be doing some isolation equipment here in a few weeks. And the velocities are as high as 50 meters a second, and they can handle multi-directions. I think that we should add to that the answer to the question there.
Thank you, Jim. Oh, go ahead.
If you're interested, they should come to the presentation that will take place. I think you have individual sites, and they could also have office hours with our research engineer that can answer additional questions.
Thank you, Jim. And yes, and Gilberto, thank you for your responses. And all of the information is also available on FeedLoop, and on the Design Safe webpage, you'll also get more information about all of the sites. So we're going to take one more question from Madeline, who's here in person with us.
Hi, yes, one more question directed at the RAPID facility. So for Jeff, anyone feel free to jump in if we're going to get into this later, but I was just thinking in terms of writing grant proposals that involve RAPID facility elements, do you have any advice for how to do that, in the sense that these are 4 events that haven't occurred yet? So I feel like some of the language surrounding that might be a little vague. Do you have any suggestions for how to work that in?
Yeah, we can certainly talk more about that in office hours. I think it's it's a challenge that we certainly face, and this is not the first time we've had the question. We really like to have proposals that are, multi-year proposals as opposed to just rapid grants. We do support a lot of individual rapid grants for, post-disaster reconnaissance as well. Those obviously, have the timing all down, right? And so those are easy to write from that perspective. I think there's I think there are ways to make sure that, you want the review panel not to question whether or not you're going to actually be able to achieve the objectives, right? So that's the goal. There are ways to make sure that happens, right? Does it need to be, category 3 hurricane, right? Do you need, that levels of wind speed to be able to go out and do what you want to do? Or, will some tropical storms suffice? And, so we just need to walk through kind of the what your research objectives are, right, for your particular project, and determine kind of maybe a couple different ways to achieve those with field, with the field campaign. One thing to think about too is that these could be global events, right? And so like, you don't have to deploy in the US. We've got a lot of experience sending researchers with our equipment all over the world. So, I think you can make a compelling case. It is a challenge though, and something that you need to think about quite a bit, because I think we have had cases where, review panels have said, well, why are we going to give you this money when, it's unlikely that what you're proposing is actually going to be able to happen. So we just need to walk through and manage that kind of from a risk perspective almost, and make sure that there's a clear path to achieve your research objectives, even if there's not the signature event that your research may ultimately focus on mitigating, but does it have to be that signature event to make some really good progress? So we can talk a lot more about that in office hours.
Perfect. Thank you.
Yeah.
Wonderful. I want to thank all of our representatives for being available today. And I know that people in the room have signed up for different office hours, perhaps prior to coming, but you'll also have an opportunity to sign up later this afternoon if questions have occurred to you. And as you get into your proposal groups, you may have some questions that occur to you then. That's sort of the opportunity we have as you're digging into something that you might want to try. Well, this is actually a question now that pops up that I understand that I should be asking. So thank you again to all of our site representatives for answering these questions so well. And we'll look forward to seeing you throughout today and tomorrow as well.